Good morning, everyone. Welcome to Berlin. I'm Xiaowei. I currently lead the real-time data infrastructure team at Alibaba. Today, I will talk about how we build a unified data process engine, which is good at both stream and batch processing. First, I would like to offer some background on Alibaba. Alibaba is has the world's largest e-commerce platform. It includes Taobao, Tmall, AliExpress. It also has a logistic division, Cainiao Logistics, which provides logistics service to Alibaba Group. And Financials is a financial company which is affiliated with Alibaba. Well, Alibaba is also a big player in cloud business. Ali Cloud is a dominant cloud provider in China. As you can imagine, with such a large and complex business, we generate tons of data. To give you some feeling of the amount of data we generate, here are some statistics. The total amount of data we have are many exabytes, and it grows by petabytes every day. We generate over 1 trillion events a day, and our platform processes 472 million events a second in a second at the peak last year. So in the background of this slide, what you see is a real-time dashboard for Tmall on Singles Day, which happens on November 11th every year. Singles Day is the largest shopping festival in China. It is kind of similar to Black Friday in the United States. On this day, a lot of things go on sale for 50% off. So people are buying a lot of stuff, and there are tons of transactions going on. And to give people a good sense of how things are going, we provide a real-time dashboard which displays the total amount of transactions until that moment. And this is what you see in the background of this slide. This is just one example of the real-time data processing pipelines. In production, there are thousands of such real-time pipelines, ranging from real-time data analytics to real-time machine learning jobs. In total, they processed 472 million events a second at the peak in last year's Singles Day. And we were able to maintain a sub-second latency in these jobs. A lot of our jobs are processing sensitive financial data, and we were able to make sure every transaction or event gets processed, and gets processed exactly once due to Flink's architecture. We were able to provide high availability and fast failover to our jobs to make sure our business is running smoothly. But real-time data processing is just one of the data processing scenarios at Alibaba. We also have needs for other types of data processing. And I would like to classify these scenarios into 3 buckets. On the left side, what we can see is the stream processing. The nice thing about stream processing is that it can offer results with very low latency. But the flip side is it requires the query to be fixed. On the right side, we see the other extreme, which is the traditional batch analytics, in which case you can pretty much run any queries, but it will take you longer to get the results. Somewhere in the middle, we have something what I call progressive processing, which includes continuous or periodical batch jobs. One of the key insights by the early founders of Flink is that streaming can be the core abstraction behind all these types of data processing. And everything can be treated as a special case of streaming. For example, batch processing can be treated as a special case of streaming in which the input streams happens to be finite or bounded. The hope is that by using streaming as the foundation, we can build a unified engine which is good at all these different data processing scenarios. Let's take a look at where we stand today. This shows you an architectural diagram for Flink. At the bottom, we have the cluster management system. Flink can be deployed in many different environments. For example, it can be deployed locally in a single JVM. It can run in a standalone or young cluster. Flink can also work in a cloud environment such as GCE or EC2. On top of that, we have Flink runtime. Flink's runtime is the component that runs a distributed streaming data flow program. It's responsible for scheduling the tasks in this program and managing the states for these tasks, do the checkpoint, and do the recovery in case of failures. Flink's runtime is the key component which can provide exactly one semantics and high throughput while maintaining very low latency. On top of Flink's runtime, we have the API layer, which includes the data string API in the case of string program, and the dataset API in the case of batch programs. Let's take a closer look. The first thing we notice is that now we have two sets of APIs. So the unification is already broken at the API layer. And if we take a look further into the implementation of these APIs, we will notice that a data stream program basically consists of a bunch of string transformations, which gets translated into a string graph, which gets compiled into a job graph. On the other hand, when we have a dataset program, batch program, it has an operator tree, which gets translated into a batch plan. Optimizer looks at the batch plan and picks an optimized plan, which gets translated into a job graph. So we can see that at the API layer, there are already two distinct code paths for streaming program and batch program. And you would have thought that these two programs probably start to merge at the runtime layer because now they all go through the job graph, which is shared by both streaming and batch. Unfortunately, that's not true either because in the case of streaming, the job graph is executed by a bunch of string tasks and string operators. But in the case of batch, the job graph is executed by batch tasks and drivers. So again, the code path is different for streaming and batch. This is what we see here. So there is certainly some gap between the current state of Flink's code and our vision of a unified engine. And we wish a lot more code could be shared between streaming and batch. Let's take a look at where we stand for each scenario. If you look at the stream processing engines out there, there are actually quite a few choices, including Storm, Kafka streaming, Spark streaming, and Flink. I think it's fair to say that in terms of both functionality and performance, Apache Flink is by far the most sophisticated open source stream processors out there today. This gave us a very solid foundation for streaming for a unified engine. At the batch side, there are also a bunch of choices for batch execution engines out there. So the key question is, can we leverage the solid foundation Flink had in streaming and build a unified engine which is also good at batch processing? Before I answer that question, I would like to show you a quick study a couple of years ago by some research. I think it's also in Flink Forward. From this diagram, you can see that this is actually a batch benchmark. This is the TerraSort batch benchmark. In this benchmark, we can see Flink performed the best among all these different engines. The key insight from that study was that Flink's streaming approach to batch processing allows us to overlap the first stage and the second stage of processing, which allows us to overlap the usage of disk and network together with CPU. This more efficient use of resource gave Flink an advantage in such a batch benchmark. So from this small study, there is some good evidence that by building a unified engine on top of streaming is not only feasible, but may actually give us an advantage in batch processing as well. In the rest of this talk, I will share with you the journey we went through at Alibaba in building such a unified engine on top of streaming. I will talk about it from 3 dimensions: the functionality, the performance, and reliability. First, let's first look at the functionality. When we build a unified engine, we first want to have a unified API as well. To that end, we decided to go with SQL. In addition to be a unified API, SQL also have a few other advantages. SQL is declarative, which means instead of telling the engine exactly how to do the computation step by step, a user only needs to tell the engine what the correct result should be. The engine has the freedom to choose the optimal plan to execute his computation. This not only allows the engine to have more efficient ways to do the computation, but it also greatly lowers the bar to develop data processing programs. Your project may have multiple people working on it, and it's because SQL is a commonly understood language. If we use SQL as the API, it will become much easier for people in your projects to communicate with each other and improve the efficiency of communication. SQL is a 40-year-old language, and it has become pretty stable by now, which means you actually have the freedom to upgrade your engine or even change your engine without disrupting your user. And this is a freedom we took advantage of at Alibaba last year when we migrated from our streaming programs from an internally developed stream processor to Flink last year. And finally, but very importantly, SQL can serve as a unified API, which works for both streaming and batch. The semantics of SQL in the case of batch processing is straightforward, but we still need to define the semantics of streaming SQL. To do that, we decided to extend the concept of a table, which is usually considered as immutable in the case of batch processing, to dynamic tables. A dynamic table is basically a table whose content can change over time. In a stream processing program, you may have several string inputs. And for each input, you can conceptually consider the records in the string to be updates to a dynamic table. So you get a bunch of dynamic tables whose content changes over time. Then you can treat your SQL statement as a continuous query which runs on this set of input dynamic tables. The result will be another table whose content changes over time, which is the output dynamic table. And if you look at the changelog of this output dynamic table, you get the output result stream. This defines the semantics of streaming SQL. The beauty of this approach is we are defining the semantics of streaming SQL using the semantics of batch SQL. So the results of these two modes are guaranteed to be consistent with each other. For example, you can run your program in a batch mode, then run your program in a streaming mode, and their results will be guaranteed to be equivalent to each other. This gives us a very nice definition for the semantics of streaming SQL. The next thing is to make sure we implement all the functionality of streaming SQL. And this is what we did. We worked closely with the community in the last year or two to add a comprehensive support for streaming SQL. Today, if you look at the Flink's implementation of streaming SQL, we have string-to-string table joining. We have aggregation support. We even introduced the concept of retraction into aggregation. There is a comprehensive support for windowing. Users can express their application logic in UDX. And we added support for DDL. And there is already a rich set of connectors available in Flink SQL today. So what about the situation in the case of batch processing? If you take Flink's latest build and try it, you will find that TBCH actually works in Flink today. If you look at TBCDS, though, you will find that only half of the query compiles and runs in Flink. This is certainly some work needs to be done to get the functionality completed on the batch side. And this is what we did at Alibaba. With our work, we were able to run TPCDS without any modification of the SQL. Even further, we ported or added over 2,000 high-quality SQL test cases into our branch to make sure that the functionalities implemented by our batch is really complete. More interestingly, the same set of tests can be run in our streaming mode, and we were also using it to check the completeness of our streaming SQL implementation. Let me explain what we did in implementing such a unified engine that has complete support for SQL's functionality. Let me talk about it from two layers. The first layer is from the runtime layer. Then I will talk about the SQL layer. So first, look at the runtime layer. And this is the current execution model for Flink's runtime for both stream program and the batch program. There are two key differences between these execution models. The first one is the push versus pull. In the execution model for streaming, we use the push model, which means the input records gets pushed to the stream operator. On the other hand, a batch operator will actually pull the records from the inputs. This is the first difference. The second difference is that a streaming operator does not care about in which particular order the input records gets processed. But on the other hand, a batch operator may care a lot about the ordering of how records gets processed. For example, in this picture, we see a hash join operator. A hash join operator has to process all the records from the build side, build a hash table before it can process a single record from the probe side. These two major differences is the fundamental reason that Flink has different code paths for streaming and batch at runtime. So we decided to fix that by introducing a unified operator framework. There has been a lot of research in push versus pull in the domain of query processing. And there are pros and cons in each approach. But the important thing to remember is that Flink has been extremely successful at streaming. So whatever choice we make had better to be closer to the streaming model. Because of this, we decided to adopt the push model in our query processing, the same way how we did in streaming today. But we extend the functionality of stream operator to allow it to choose the order of how inputs are getting processed. After the operator processes every record, it can tell the framework which side of input it wants to process next. It can tell the framework it wants to process next record from the left side, or process next record from right side, or from either side. In this way, it's very easy to implement the logic of a hash join operator in this new unified operator framework. And one more thing you probably notice is that there has been a long-wanted feature in stream processing, which is side inputs. With this extension of operator framework, you can express the logic of side inputs easily in this new model. Of course, to get side inputs really working, you also need to do some work to make sure it interacts with checkpointing correctly. But the key lesson is that by taking a unified approach, it not only benefits batch, but it also benefits streaming. This is a lesson or key observation we see over and over again. Now let's take a look at the SQL side. This is the current architecture for Flink on the left side. So when a user writes a table API program or a SQL program, it gets translated into a data stream program in the case of stream processing, and gets translated into a data set program in the case of batch processing, there are two problems in this current approach. The first problem is that when we implement some functionality in SQL, we may be forced to add some API in either the data stream or dataset program. This is not only tedious, but sometimes the requested API should not really be public. The second problem is that the SQL has a query optimizer, but a dataset program also have an optimizer built into it. When you have two optimizers, it's like a person having two brains. Sometimes they may think differently, and this can be problematic. To fix this problem, we decided to have some modification of the current architecture and introduced a new commonly shared component, query processor. A query processor has two subcomponents within it, a query optimizer and a query execution. On top of the query processor, we have the API layer, which consists of table API, the relational APIs, such as table API and SQL. In addition, the traditional dataset and data stream API can also take advantage of this new query processor. Let's see how it works in action. A user writes a table API or SQL program. We look at some pluggable catalog and construct a logical tree, logic plan represents this SQL. A planner or query optimizer, in the case of Flink, which is implemented, in the case of Flink, it is implemented in Casite. It takes a bunch of optimization rules. The one nice thing about Casite is it allows you to extend it by adding arbitrary optimization rules. With this set of optimization rules, it applies these optimization rules, get all possible execution plans, and finally, it will choose an optimal physical plan. The physical plan gets copied out and eventually gets transformed into a job graph, which can be executed by Flink's runtime. In this new code path, the batch processing, batch SQL, and the streaming SQL will share the same code path in this new approach. Even further, you can imagine that a dataset API can also construct a logical tree, which gets optimized by a planner and choose the best physical plan to execute it. The data stream program is a bit different in the sense that a data stream program is more physical, and you do not need optimizations for that. So in the case of a data stream program, you can directly translate it into a physical plan without going through the optimizer phase. So in this new approach, we not only allowed code reuse between batch and streaming SQL, but different flavors of API also can share a lot of code in the query engine. In this way, we were able to implement a unified engine which supports all functionalities in batch SQL and streaming SQL. Next, let's talk about performance. It's hard to talk about performance without first showing you some numbers. This is from the TPCH benchmark. The white bar represents the numbers from Flink, which is the name for the internal version of Flink that we developed at Alibaba. And the gray bar represents Flink 1.6. As you can see from this picture, Flink performs significantly better than Flink 1.6 in TPCH benchmark. In fact, on average, Flink is 10 times as fast as Flink 1.6. This is an improvement by an order of magnitude. Let me explain how we did that. The first thing we noticed in batch processing is that Flink's scheduler is not very sophisticated at scheduling the operators in batch mode. Sometimes it schedules the operator, but the operator sits there doing nothing, wasting resource. For example, in the same hash join use case, the hash join operator cannot do anything with the probe side until it processes all records from the build side and finish building the hash table. But in current version of Flink, it will schedule all these three operators at once. So what we are having is the operator on the probe side will be sitting there doing nothing, waiting for the hash table building. This is certainly not optimal. And we fix that by introducing customizable scheduling in Flink's runtime. This new functionality allows the high-level components, such as the query engine, to tell the runtime when to schedule each operator. So in our case, the query engine will ask runtime to schedule the build side and the hash join operator first. Let it process all the build side, finish building its hash table before it asks runtime to schedule the probe side. In this way, we make much better usage of resource and give us a performance boost. For anyone who tries to optimize a program, you probably know that inlining is one of the simplest yet most effective way of doing optimization. Chaining is the analogy of inlining in distributed environment. Flink was pretty good at chaining, but there are still some limitations in Flink's chaining implementation. Any operators with multiple inputs cannot be chained. So if you look at the graph on the left side, it's broken down into 5 different parts, because operator A and operator B both have 2 inputs. In Flink, we removed this limitation and allows operators with multiple inputs to be chained. So in this particular graph, the whole thing can be chained and executed in a single task. The savings can be significant when this happens. Once you enable chaining, it opens the door for another optimization, which is object reuse. But there is a caveat with object reuse. You need to make sure, the operator has to make sure you don't modify the objects. Here comes another advantage of SQL. In SQL, the operators are not implemented by the users. The operators are implemented by the framework itself, by Flink itself. So in our implementation of SQL, we can make sure the operators does not modify such objects, and we were able to turn on object reuse, which gave us a significant performance boost as well. With these changes in Flink's runtime, we were able to double the performance of our query processing. Next, let's take a look at the query execution engine. For query execution, one of the significant performance overhead is actually in serialization and deserialization. Constructing objects in Java can be expensive. It also adds a lot of stress to garbage collector. To fix that, we decided to introduce a binary format which makes serialization and deserialization trivial. Our binary format is, also allows us to access individual columns very efficiently. In addition to this binary format, there are a bunch of other optimizations that we have done in the query execution engine. Our query execution engine, our expression will operate directly on such binary data. We make extensive use of JVM intrinsics. And we code gen not only expressions in operators, but we also code gen some important functions such as partition functions. We code gen all our operators. We introduced the hash aggregation operator. We improved the hash join operator. We added support for semi and anti-join operator, as well as a bunch of other interesting operators, which which gives our query optimizer better plan choices. We optimize the resource usage in our operators. Instead of spreading the memory across all operators evenly and not be able to really use it, we use statistics to calculate, to estimate how much memory an operator needs. Even further, the operators will allocate the memory on demand instead of allocating it ahead of time and then wasting some of the memory. By doing all these changes in the query execution engine, we were able to, again, more than double the performance of our query processing. Finally, let me talk about the query optimizer. There has been extensive improvements we made in the query optimizer. Our query optimizer is completely cost-based. We use cost to decide the ordering of join, the type of join, the strategy of doing aggregation, such as if we want to use two-stage local global aggregation versus one-stage aggregation. We introduced a bunch of advanced rules in our query optimizer, such as subplan reuse or unnecessary shuffle removal. Our query optimizer relies on rich statistics for good cost estimation. These statistics include minimal, max value, null count, or NDV. And in the future, we are looking forward to adding histogram support into our cost model as well. With these changes in query optimizer, we doubled the performance of our query processing again. So, to summarize, the 10x performance we are getting comes from improvements in all three major components, from Flink's runtime, the query execution, and the query optimizer. One thing I would like to point out is a lot of such optimizations not only benefits batch SQL, it also benefits streaming SQL. This is the beauty of our unified approach. Finally, let me talk about reliability. In any large-scale deployment, we need failure inevitably happens. And we need to make sure when failure happens, we can recover from such failures quickly at relatively low cost. To do that, we need to make sure the granularity of failover is as small as possible. In last year, we worked with the community to implement region-based failover support in Flink. But to get it really working in batch mode requires a lot of additional work. And we did such work. In addition to this, we improved the story of job manager failover. So when job manager fails, we no longer need to restart the whole job and start from scratch again. The job manager can restart by itself and continue from there. We are also looking, and we also added blacklist support. So if we observe some machine fails repeatedly, we can blacklist the machine. A streaming mode of shuffling or network-based shuffling is great in that it gives you very good performance. But file-based shuffling also have its advantage. The failover will be faster in the case of file-based shuffling because it reduces the failover region. So it's also important to have a good implementation of file-based shuffling. In the current implementation of file-based shuffling in Flink relies on task manager to do the job, which simplifies the deployment, but there is one downside with it. Even after all the tasks finish in this task manager, the task manager cannot exit. So additional resource will be taken when this happens. We introduced external shuffling to fix this problem as an addition to our shuffling mechanism. So we had a tight integration with the Jiang's shuffle manager for our external shuffle service. With such an implementation of file-based shuffling, in the future, our query optimizer can strike a balance between faster execution in normal mode and faster recovery in the case of failure by inserting file-based shuffling at appropriate places in the query plan. We are also looking at asynchronous mode, which means in the normal execution, we will use stream-based shuffling, network-based shuffling, but at the same time, we will write records asynchronously to an external shuffle service. So in the case of failover, we can use the external shuffle service to do the recovery. In this approach, it will give us the best of both worlds. We will have a good performance in the normal world, in the normal execution, but have a fast failover in the case of failure. If you want to know more details, there is a talk by Feng from Alibaba this afternoon on runtime improvements for Flink's batch processing. You are welcome to go to the session. So with all this work, we were able to build a unified engine on top of the strong foundation laid out by Flink's stream processor. But we want to go one step further. We want to blow the boundary between stream processing and batch processing, or even eliminate the distinction between the two. What I mean is this. When you have a stream program, if you are in a catch-up mode, for whatever reason, your inputs get backed up, the query optimizer can potentially switch your execution into a batch plan, which allows you to do a catch-up in much more efficient fashion. After things get caught up, the optimizer can switch back to the streaming plan, which gives you low latency. On the other hand, you may have a traditional batch program. For example, you may have a batch program that calculates the statistics, the daily statistics for a huge amount of data. Usually, this batch program cannot start until the day finishes, until all the data arrives. But if you have tons of data, the computation itself can take many hours, and sometimes you may miss the deadline for your business. When this happens, it's possible that our query optimizer can actually choose a streaming plan for such a traditional batch job. So the computation can start during the day when data arrives incrementally. And the streaming plan will update the results incrementally. When the day finishes and all data arrives, the streaming plan will be able to produce the result very quickly, meeting your SLA. More and more data processing. This is what I refer to as the grand unification of data processing. The distinction between batch processing and stream processing is not that clear anymore. And we can have a plan that dynamically switch between these two modes. Nowadays, more and more data processing is related to machine learning and artificial intelligence. We need to make sure our experience for machine learning and AI is great. So we are looking at improving the experience for PY Flink, enhancing table API to allow users to write machine learning programs easier. We are looking at deep integration into some deep learning frameworks such as TensorFlow. We are adding lots of traditional algorithms to Flink's ML. Here's a quick summary. Flink is already the best open source stream processors out there, and it is becoming the best open source batch processors as well. Our unified approach based on streaming really benefits both batch, and streaming. And finally, we are working on seamless experience for machine learning and AI workloads. Finally, I would like to, here is my plug for Flink Forward China. On December 20th to 21st, the first ever Flink Forward China will be held in Beijing at the National Conference Center. It is a joint effort by all the major players in the Flink community from China. And you are welcome to submit your talks. And I look forward to seeing some of you guys there. Thank you.